Hi. Let's use APL to make sure that all our odd numbers become even numbers, doing so by incrementing them, making them one larger. That is, 3 would become 4, and negative 3 would become negative 2. Let's start off by defining an array A, and we're going to give it the numbers from 1 to 16 for now. And we can then take the array, execute it, we get this. We can also modify this assignment and subtract a bit. So let's subtract 5. Okay, now we've got some negative numbers and some positive numbers. Let's further modify this by shaping it into an array of shape 4 by 4. Here we go. Good. This is some good test data. We're going to write our first function, which is going to solve the problem. Let's develop it piece by piece. This is a function. It's enclosed in braces to mark its limits, and omega refers to the right argument, because omega is the rightmost letter of the Greek alphabet. So this is an identity function. It doesn't do anything. Now we can divide by 2 to kind of scale down, and we can see how APL's arithmetic automatically maps to all the elements of an array, even a multidimensional array like this one. If we now round up, that will add a half, and we've scaled down to half the magnitude that we had before, which means we can then scale back up again to the full magnitude, and we will have added a whole number rather than half to all the odd numbers, which gave us 0.5 as decimals. Of course, the even numbers, we divide them by 2, it gives us a whole number again, and then rounding up is not going to do anything. So here's the rounding up, which uses a function that's the same symbol as the left side of the special brackets, the rounding up brackets, ceiling brackets, used in mathematics. But in APL, every symbol it stands on its own, is a function on its own, and take everything on its right as its argument. So we don't need any parentheses here either. The round up or ceiling function, which kind of looks like a wall with a bit of a ceiling, takes everything to its right, that's omega divided by 2, as its right argument. And now we can continue with multiplying by 2, and this gives us the result that we are looking for. All the odd numbers became 1 greater, and all the even numbers stayed the way they were. So we can give this a name, f, and we can apply f to a, and like this, no parentheses or brackets or any sort necessary to apply this function. So this is one way of solving the problem. Let's take a different way of solving the problem. We mentioned briefly here that the odd numbers, they give a half as decimals when divided by 2. So that would be the remainder when divided by 2 that has already been divided by 2 that gives us a half. And we can exploit this by taking the remainder when divided by 2. We write that with a vertical bar, which is borrowed from mathematics as divides. Right? So instead of saying that 2, instead of expressing the predicate that 2 divides omega, we are asking what is the remainder when 2 divides omega. And so we can see that all the odd numbers, they give 1 as a remainder. And that's great, because what we want to do is take and add 1 to all the odd numbers, and add 0, so to say, leave them as they are, all the even numbers. So we can just take all the numbers and add their remainder when divided by 2, and that gives us the result that we want. So let's call this g, and we can apply it with g of a. So here are 2 really neat solutions to our problem. Thank you for watching.